So section 9.1 talks about probabilities. And so we have something called an experimental probability. It says probabilities are expressed as ratios, expressed as fractions, decimals, or percents, and determined by considering results or outcomes of an experiment. It says an experiment is an activity whose results are outcomes of the experiment. For instance, if we toss a typical coin that cannot land on the edge, there are two distinct possible outcomes. We can either get heads or tails. So it says the set of all possible outcomes from an experiment is what we call the sample space. Okay, so the outcomes of the sample space cannot overlap. In a single toss coin, the sample space S is given by the set H and T, where H represents heads or T represents tails, right? It's either going to be one of those two. It says the sample space can be modeled by a drawing, what we call a tree diagram. It says in a tree diagram, each outcome of the experiment is designated by a separate branch. So you flip a coin and it'll either be heads or it'll be tails, right? And there's my sample set. Okay. So it says a fair die is flattened out. So they took our die, right? Remember what a die looks like? This 1, 2, 3, little cube, right? 1, 2, maybe 1, 2, 3, 4, 5. All they did is they just opened it up for us, okay? So here's a die. They opened it up so we can see all the sides. And let's see what we have. It says, suppose an experiment consists of rolling a fair die. Find each of the following. The sample space S for the experiment modeled by a drawing, modeled by a tree diagram, and listed as a set. Okay, so let's take a look here. For part A, if I was going to do, say, a tree diagram, I could either get a 1, 2, 3, 4, 5, or 6, okay? As a set, it'll be, see if I can move this over, oops, there we go. It'll be the numbers 1, 2, 3, 4, 5, and 6, right? Okay, let's see. Okay, now part A, or part B from here says the event A consists of rolling a 5. Okay, it's just going to be the number 5, okay? Part C, it says the event B consists of rolling an even number. So we can get a 2, 4, or a 6. Okay. And D says the event C rolling a prime number. So let's think about prime numbers. So 2 is prime, 3 is prime, 5 is prime, right? Remember what prime numbers are, numbers that can't be broken down anymore. So when I look at my numbers here, like I can break down 4 into 2 times 2, I can break 6 down into 2 times 3. A lot of times people ask, what about the number 1? By definition, guys, a prime number is going to be bigger than 1, okay? So the first number that's bigger than 1 here in our set would be 2, okay? All right, so it says the experimental or empirical probability of an event is the long-term or long-run relative frequency that an event will occur given many repetitions. The relative frequency is the ratio of the number of times an event occurs to the total number of trials. The relative frequency in an event can also be called the experimental probability. So it says, if we toss a coin 100 times and it lands on heads 64, we say the experimental probability is 64 out of 100 or 16 out of 25. Okay? And it says probabilities are typically recorded as simplified fractions, decimals, or percents. Okay? Now we have theoretical probability. It says we could argue that since a fair coin is marked heads or tails and it's symmetric with two sides, each side should appear about the same number of times if the coin is tossed many times. We write the probability of an outcome X or an event E as P of X or P of E. The probability of flipping a head on a single coin would be the probability of getting a heads, and they kind of wrote it right here. And the event of tossing heads and the event of tossing tails would be equally likely because we're going to be one of those two outcomes, right? So the probability of getting the heads or the probability of getting tails would be 1 out of 2, right? Because there's one heads out of the two possibilities, either heads or tails, or there's one tails out of the two possibilities, right? So I'm either going to get a heads or a tails. So I have a sample set with 2. What's the probability that I get a heads? Well, there's only one heads out of my 2 options, right? Same thing for tails. Okay, and it says, and if an experiment is only performed a few times, the experimental probability might not be accurate in predicting the probability of an event. This leads to the fact that an experimental probability only suggests what will happen in the long run. If the experiment is repeated many times, this concept is what we call the law of large numbers, or Bernoulli's theorem. Okay, so it just says here, as the number of trials in an experiment increases, an experimental or empirical probability of a particular event approaches the fixed number, the theoretical probability of that event. Okay, so definition of a probability of an event and sample space with equally likely outcomes. It says for an experiment with non-empty finite sample space S with equally likely outcomes, the probability of an event is given by, and it has a little formula here. So I'm going to walk you all through these problems, guys, so that we can figure this out, okay? So let's see if we can do a couple of examples to kind of make sense of what all those words were telling us, all right? So it says, let S be the set of the numbers 1 all the way through 25. If a number is chosen at random, that is, with the same chance of being drawn with all the other numbers in the set, calculate each of the following probabilities. Okay. A, the event that an even number is drawn. Okay, so let's list all our even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I'm going to count them now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the probability of getting an even number would be 12 out of 25 because we have a total number of 25 right there. Okay. Now, the event B, that a number greater than 25 is drawn. So think about it. We know we have a total number of 25. What's the probability that we're going to get a number greater than 25? Well, none of the numbers here are bigger than 25. So 0 out of 25 would be 0. There's no way we can pick a number that's bigger than 25 if we're only looking at the numbers 1 through 25, right? Okay. C, the event C that a number less than 26 is drawn. Well, wouldn't the set C be that set? Because all those numbers are less than 26. So if I wanted to find the probability of event C, it would be 25 out of 25, which would be 1. What's the probability that I'm going to get a number less than 26? The probability is 100% because all my numbers are less than 26. Okay. D, prime numbers. Okay, so let's think about our prime numbers. So from these numbers here, which ones are prime? 2, 3, 5, 7, 9, 10 are not, 11 is, 13 is, 14 no, 15 no, 16, 17, 18 no, 19 yes, 21 no, 22 no, 23 are all going to be our prime numbers, right? These are all numbers that I cannot break down. So let me count. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the probability of getting a prime number would be 9 out of 25. Okay. And then part E. The number that a number both even and prime. So it has to be an even and a prime number. So remember, these were my prime numbers here. And these were my even numbers here. The only number that's both even and prime is the number 2. So what's the probability that I'm going to get? 1 out of 25. Why 1? There's only one number right there. Okay. All right. So it says, if A is any event and S is a sample space, My probability is always going to be a number between 0 and 1. Okay? So my numbers will lie numbers here, and if it's between 0 and 1/2, it's probably going to be unlikely. If it's between 1/2 and 1, it's going to be likely. The probability of getting, if the probability of 0 means it's impossible for that to happen, and if the probability is 1, that means it's certain to happen. Okay. So let's take a look here. It says an ordinary deck of playing cards consists of the cards shown in the figure here. If we drew a card at random from an ordinary deck of cards, find the probability that A, the card is an ace. Okay, so let's do it like this. The probability that we're going to get an ace. Okay, so we have 13, 13, 13, 13. We got a total of 52 cards, okay? So how many cards do we have? 52. Out of those 52, how many of our aces? 4. I'm going to divide both those numbers by 4. And so the probability of getting an ace would be 1 out of 13. Okay. Now part B says, what's the probability we're going to get an ace or a queen? Well, we still have 52 cards, right? And we know we have 4 aces, and we also have 4 queens, so that's going to be 8 out of 52. And if I divide them both by 4, I end up with 2 out of 13, right? Okay. So mutually exclusive events. It says if the events A and B are mutually exclusive, if and only if they have no elements in common. Okay. And if they don't have any elements in common, then the probability of A or B would be the probability of A plus the probability of B. And it says here, if A is event, then A, the way we read that, guys, is A bar is its complement. So the probability of the A bar is going to be 1 minus the probability of A. So I know that the font's pretty small here, so I'm going to zoom in a little bit, guys. Let me see if I can do this without getting all thrown off, but it threw me off a little bit. I can go back and find it. Don't worry, we'll be right there. Here we go. Okay. So just so we can see this a little bit better. All right. So now it says a set of dolls is in a packing crate. 6 with blonde hair, 4 with black, 5 with red. Okay. So let's figure out how many do we have total. Okay. 6 and 4 is 10, and 5, we got 15 total. It says if one doll is drawn at random from the crate, what's the probability that the hair is not red? Okay. So we want to know what's the probability that it's not red. This would be the complement of red, would be not red. And I can use this little formula here. I got 2 ways of doing this. I'll show you the first way. We can say, let's find 1 minus the probability that it is red. Okay. So if I'm going to do it that way, the probability that would be red would be out of the 15. How many of them had red hair? 5. 5 out of 15 would be the same thing as 1/3. So 1 minus 1/3 would be 2/3, right? It's supposed to be at number 3 right there. Okay. The other way I could do it, if I wanted to find the probability that it's not red, is I could say out of the 15, if I know that 5 are red, then 6 plus 4, 10, would not be red. And again, if I divide them both by 5, we still get 2/3, right? So either way we do it, we're going to get the same thing. Okay. All right. Right here we have a little bit of summary of probabilities, okay? The probability that something cannot happen is 0. The probability that something will happen is 1, like that we're certain it's going to happen. The probability for any event is always going to be a number between 0 and 1, okay? So what does that mean? A number between 0 and 1, 1/2, 2/3, 4/5, 0.78. I can't get probabilities of like negatives. I can't get probabilities of 17.9. Has to be a number between 0 and 1. Okay. It says if A and B are mutually exclusive events, then the probability of A union B would just be the probability of A plus the probability of B. If there are any events, the probability of A union B is the probability of A plus the probability of B minus the probability of both. I'll explain those as we get there. And we just did the complement one right now, right? Okay, so it says a golf bag contains 2 red tees, 4 blue tees, 5 white tees. Okay. Part A says, what is the probability of the event R of a tee drawn at random is red? Okay, so let's first find how many tees do we have total. So 2 and 4 is 6, and 5 more is 11. Okay, so we want to figure out what's the probability that we're going to get one that's red. Out of the 11 that we have, 2 of them are red, so my probability would be 2 out of 11. Okay. Now, look at part B. It says, what's the probability that it's not red? Okay. So if I want to find the probability that it's not red, I can just say, let me take 1 minus the probability that it is red. The reason I want to do that is we just found this answer right now. So 1 minus 2, 1 minus 2 over 11. Guys, you can think of this 1 as 11 over 11, right? Oops. Because 11 divided by 11 is the same thing as 1. And 11 minus 2 is 9. Okay. And then part C says, what's the probability that we're going to get a red or a blue? Since we don't have any tees that are both red and blue, we're going to say, what's the probability that it's red plus what's the probability that it's blue? Well, we know that it's red is 2 11s. Blue was 4, so that's going to be 4 out of 11. And if we add them together, we're going to get 6 out of 11, right? Okay. So, the next question here just says, determine whether each of the following pairs of events are mutually exclusive or not mutually exclusive when drawing one card from a standard deck of 52 cards, okay? So think about a deck of cards, okay? So guys, a lot of times what I tell my students is, remember, your cards can be 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, or Ace. And then we're going to have this either for hearts, diamonds, spades, or clubs, right? So, I don't have the picture right here in front of me, but I want you to think about this is what my deck of cards is going to look like, right? Okay. So what we mean by mutually exclusive is, can they happen at the same time? The card is red and the card is black. Can you have both a red and a black card? No. So we're going to say part A is going to be mutually exclusive, because we can't have a card that is both red and black, right? They're either red or they're black cards. Okay, part B. A card is an even number and a prime number. Remember the number 2, it's both even and it's prime. So this is not, I'm just going to abbreviate, mutually exclusive. Okay. Part C, the card is black and the card is a club. So I don't know how many of you guys know a whole lot about playing cards. Some people see them, some people don't. So in case you haven't, let me write it here for you. These are clubs, okay? These are diamonds. These are spades. Oops, spades. And these are obviously hearts, okay? So the question said, let me scroll back down, the card is black and the card is a club. Well, if you look here, let me scroll back up, clubs are in fact black cards, so they are not mutually exclusive, because you can be, a club is going to be a black card, right? So not mutually exclusive. Part D. The card is a face card and an odd number. Well, these are my face cards, right? They're not odd numbers, so those are going to be mutually exclusive. Okay. Part E. The card is a heart and a face card. Can't these cards here be hearts as well? Yes, they can. So this is not mutually exclusive. And F, the card is a spade and a diamond. It can't be a spade and the diamond at the same time, right? It's going to be one or the other. So those would be mutually exclusive events. Okay. All right, it says for the next problem here, if you flipped a coin 15 times and got 15 heads, what's the probability of getting a head on the 16th time? Okay, remember, when you flip a card, or flip a coin, I'm sorry, it's going to be either heads or tails, right? So now we're trying to figure out what's the probability that we're going to get a heads. Well, how many choices do we got? We got, oops. Come on, pen. Sorry, guys. There we go. Oh, still frozen. Let's see. There we go. Okay. So I can either get heads or tails. How many of them are heads? One. The fact that we got 15 heads the first time doesn't, every time I do this, I still have an equally likely chance. Okay. So now it says if A and B are mutually exclusive, so remember what it means when they're mutually exclusive is that A union B, the probability of those will be the probability of A plus the probability of B. Okay. So it's asking me, what's the probability of A union B? Well, what's the probability of A? It's 0.3. What's the probability of B? Oh, it's 0.4. So the probability of either one would be 0.7. Okay. All right. Here it says when a thumbtack is dropped, it will land either point up like this or point down like that. It says the experiment was repeated 80 times with the following results. 56 pointed up was 56 and point down was 24. So point up was 56, point down was 24, and the total was 80. Part A. What's the experimental probability? Not the theoretical probability, but the experimental probability that it's going to land point up. Well, that it's going to land point up would be 56 out of 80. We can divide them both by 8. So 8 goes into 80 10 times, and 8 goes into 56 7. Okay. Part B. What's the experimental probability? Again, experimental. That it's going to land point down. 24 out of 80. Can divide them by 8 again. That's 3/10. Okay. Now, part C says, if we were to try the experiment another 80 times, would we get the same results? No, we wouldn't expect to get the same results, right? Because the point up and point down, right, whether it's point up or whether it's point down, it's just like getting a heads or tails, right? There's an equally likely chance. Okay. And let's see. Would we expect to get the results, the same results on it? No. Again, no, because there's still an equally likely chance. We should be coming up with like 50-50, roughly, right? All right. Okay, so it says a bag contains n cards, each having a natural number less than or equal to the number n on it. So let's think about what that means. It means we're going to have numbers like this: 1, 2, 3, 4, 5, 6, dot, 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 all the way to n. Okay. It says the probability of drawing a card with a number less than or equal to 10 is 4/10. How many cards are in the bag? Okay. So first thing is, we don't know how many cards are in the bag, but we know the probability is going to be 4/10. And we're going to pick a number that is less than or equal to 10. So less than or equal to 10. How many numbers are less than or equal to 10? 10 of them would be. Okay, now we want to just solve this. We can do a little cross multiplying. So n times 4 would be 4n. 10 times 10 would be 100. We divide both sides by 4. We end up with 25, right? Okay. All right. So now it says, suppose we have a box that has 5 white balls, 3 black balls, and 2 red balls. Okay, so let me think about that for a minute. We got 5 white, 3 black, and 2 red. So my total here is going to be 10. The question says, is it possible to add the same number of balls to each color box, of each color to the box, so that when a ball is drawn at random, the probability of an event that a black ball is the following? Okay, so we're going to add, we want to know, can we add the same number of balls to each color? So right now we have 10. Okay, how many different color balls do we have? We have 3. So we're going to add 3 of the same color, whatever that number is. Like whether we're going to add, like, say, 2 white balls, 2 black balls, 2 red balls. So the x is going to be the number of balls that we're going to add. So now we're going to have 10 plus 3x total. Okay, because I'm going to add x to these, x to these, x to those, whatever number that is. And we want to know, what's the probability that we're going to choose a black ball? Well, how many black balls do we have? We have 3. But remember, we're adding a certain amount to each of those. And we know, is it possible for that probability to be 1/3? Okay. So again, I'm just going to cross multiply here. So 1 times all of this would just be 10 plus 3x. 3 times all of this would be 9 plus 3x. But I want you to notice what happens when I subtract 3x on each side. I get 10 equals 9. No solution. Can't do that one. Okay. All right, I can't do that one, but maybe we can do, maybe we can do part B. Okay. So part B, I'm going to set it up the same way. 3 plus x over 10 plus 3x is going to be equal to, I want to say part B said something like 0.32. Yeah. Just move that out of the way. Okay. 0.32 all over 1. Okay, so let's multiply. 1 times all that will still be 3 plus x. And let me grab my calculator again. Okay, turn it on. Clear it out. Okay, so 0.32 times 10, moved it too far, here we go. 0.32 times 10 is 3.2. Okay, so 3.2 plus 0.32 times 3x. 3 times 0.32 is 0.96x. Okay, so let me subtract this on both sides. Okay. All right, so 3, I want you to think about it this way. Think of that as $1 minus 96 cents. How much do I got left? 4 cents. Okay. 0.2 divided by 0.4. Okay. And 0.2 divided by 0.04, I should say, 5. Yeah, this was a 0.04. Put the point in the wrong place, guys. Sorry about that. And we came up with x is equal to 5. So we could add 5 of each color, and then the probability of getting one that would be black would be 0.0 or 0.32, right? All right. Let's see. It says events A and B are from the same sample space, and the probability of A is 0.8, probability of B is 0.9. Could these be mutually exclusive? Well, let's think about this. If they were going to be mutually exclusive, then we know that this would be the case. Okay. But if I take 0.8 and I add 0.9 to it, I get 1.7. Remember we said about probability? It has to be a number between 0 and 1, and that's more than 1. So they would not be mutually exclusive, right? All right, it says Ian and Sophia flip a fair coin 10 times and record the results. They find that the coin landed on heads 8 times. And Ian says this means the coin will land on heads 80% of the time. Sophia says, I don't think so. If we flip it many more times, our results should be closer to landing on heads about 50%. Who was right? How would we know? So remember, when you flip a coin, it's either going to be heads or tails, right? So guys, even if out of the 10 times, 8 times it landed on heads, doesn't mean that that's always going to be the case, right? Remember, the probability of getting a heads is 1/2, 0.5, same thing as 50%. So who's right? Sophia, because that's our theoretical probability, right? All right. It says a student observes the following spinner and claims that the color red has the highest probability of appearing because there are 2 red areas on the spinner. What is our reply? Is that correct or incorrect? And we would say no. The one that's going to have the highest probability would be getting a green because it has the bigger area, right? So it doesn't matter that there's 2 red areas. Those 2 red areas are smaller than the one green, right? And that is 9.1.